All right, folks, this is a video explaining some of the hidden connections between some calculations that the AP will expect you to know, and I think they're important too. Okay, so question number one, um, how do you think the launch angle affects the time in the air? So, this is my question for you. Which variables, check all that apply, affect the time in the air? Okay, so oops. Here it is. All right, so we are going to launch this at a small angle, 25 degrees, fire in the hole, kind of pay attention how much time there is. Actually, we could measure that. So time does not seem to be wanting to record that. If we increase the angle, then hopefully that makes sense that it is spending more time in the air because it's going to take gravity longer to take away all of the velocity and bring it back to the ground. So the maximum hang time would be to spend all of your velocity fighting gravity, boom, boom, boom. And again, I don't know why that's not working, but hopefully that makes sense to you. Okay, so variables that affect the time in the air are, oops, that's not my Cami one. The initial vertical velocity, absolutely, because that's what's fighting gravity, even though you're comparing a velocity and a force, so don't say that. um, Initial horizontal velocity, absolutely not, right? You're fighting gravity, which is vertical, but the acceleration due to gravity. So if you were doing this on another planet, your hang time, for example, on the moon, which is not a planet, but the hang time on the moon is much more because it's going to take gravity longer to take away all your vertical velocity. Because remember, how do you determine the time at the peak? It's when Vy equals 0, and then for a symmetric projectile, you're just going to double that to find the total time. Okay, so that's what affects the time in the air, vertical velocity and acceleration to gravity. Okay, and then second question is, now instead of wanting the football to spend a lot of time in the air, if you want the football to go far, what variables do you think affect how far the football travels down the field? Okay, after you've made your guess, let's see, we'll clear this. Now I'm going to reduce this so that it's all in sight. Okay, so now same speed. Now we're going to pay attention to how far it goes. I don't know why this is not telling us what the values are. Um, Whatever. Okay, so, oh, look, it only went this far. Did not go very far at all. All right, so let's increase the angle. Went a little bit farther. That's looking good. Increase the angle. Yay, went a little bit farther. Increase the angle. 45 degree. Okay, this is not big enough. All right, sorry. I'm going to have to, that's just too wimpy. Okay, let's start at 25 degrees over again. All right, so it went this far. I increase the angle. You might expect it to not go as far right now because I'm launching it more up and less over, but watch what happens. Ooh, yay. Not only did it go farther, it hit the target. And then I'm going to increase it to 35 degrees. That's odd. It went even farther. Okay, and then I'm going to send this to 45 degrees. The magic 45 degrees is boom. That is the farthest because now when I send it up, well, so I'll just kind of give away the answer. The reason it went farther at 45 is that when you launched it too low, even though it had a lot of horizontal velocity, it hit the ground too soon to take advantage of that. And so you needed to give it a little bit more time in the air without taking away too much of its, I'm going to call it forward motion or its Vx. And at 45 degrees, the Vx and the Vy are the same. right? It's a isosceles triangle. So you have time in the air, but without taking away too much of the forward motion. But so then after you increase it, you're like, well, that was working for me. Let me keep making the angle steeper. Then you're sending the projectile more up than you are over. And because clearly if you launch it straight up, what's your range? Your range is 0. Okay, so hopefully that wasn't too, oh, we went the Cami one. Okay, so, but this is what is counterintuitive. So even if you're like, I get that, we think range is completely horizontal, but the formula for range is how far did I go? And x naught is 0. So it's really, what's important is your over velocity, your v naught cos theta, but also how much time you spent in the air. And if you remember, we just decided that time in the air was determined by v naught y and g. So what's important for the range is the vertical to get hang time, the horizontal to just what I call cover ground, and what planet you're on, because that's going to affect the hang time. Okay, so everything is important. So 45 degrees yields the maximum range, because the range is a horizontal calculation where it's the v naught x times the hang time. So to maximize the range, you want this to be as big as possible and this to be as big as possible. But as v naught x goes up, v naught y goes down. And as v naught y goes up, v naught x goes down, right? Because you've got you're keeping the speed constant. So as you dial it up, one way, then you gain vy at the expense of vx. So the best solution is to make them the same, which means the launch angle is 45 degrees. Okay, so couple more things. This is a classic picture of what I did with the animation, but one more thing is if I launch it at 15 degrees, it is the same distance as 75 degrees. This one gained a lot of ground every second, but was only in the air for a short amount of time. The purple one wasn't gaining very much ground per second, but it was in the air for longer and got to the same spot, right? Because the range is v naught x times t. So the turquoise one or the blue one had a larger v naught x. The purple one had a larger t and a smaller v naught x. So they ended up in the same spot. All right, so the other concept that you need to know is any two angles that add to 45 degrees will yield the same range. But so that's an important concept, because I think there's some good hidden physics in it, right? Of what are the variables, and there's some hidden variables that affect the time in the air. Okay, so I'm sorry I don't have a slide deck for this, so just write this down. Any two angles that add to 45 degrees yield the same range. 45 degrees is therefore the max range. That's the green one. The steeper the angle, the more time it spends in the air, which hopefully is obvious if that's a multiple choice question. But what may not be obvious is sometimes they may say, here's two projectiles. Which one's going to go the farthest? Whichever is closer to 45. Doesn't matter whether it's higher than 45, less than 45, whichever is closer to 45 in either direction is going to go farther. Okay. And then the last thing I want to say, I'm looking for a slide with some room. If something is launched from a cliff that is not 45 degrees is not the maximum range. So this shows up sometimes because they're trying to trick people who just memorize 45 degrees. And to solve this, you need some, I don't even know if calculus works. Anyway, let's say you're launching the projectile from a cliff, then what you'll find is you've already got some free hang time from the height. So you don't need as much Vy. So you can get more, you can shoot it down a little bit lower because the cliff is going to give you some of that hang time. So if the projectile has an initial height, the max angle is something less than 45. Clearly not too extreme because you do want some height. And again, what you do is you'd have to write, and I think I tried this once, and the calculus was not easy because you have sines and cosines multiplied. So there's no way they're going to expect you to solve that, but on the AP, but conceptually it's good to know. You would write range as a function of theta, and it would have sines and cosines, and then you would take the derivative of that with respect to theta. Sorry, I'm running out of, you would take dr d theta and set it equal to 0 to solve for the theta that would yield the max range. Okay. So you could probably do it in Desmos, but doing it by hand is a little bit time consuming. Okay, just a couple of different warnings about 45 degrees and maximum range that is kind of part of the canon of projectile motion. So hopefully this all makes sense, and do some practice.